Okay, let's have a look at question 4, which is showing the path of a tennis ball after bouncing on the ground at point A and hitting a vertical wall at B. The ball is travelling horizontally as it hits the wall at B. Air resistance is negligible, so it's got no effect on the motion of the ball. And it's now asking you to explain why the horizontal component of the velocity of the ball remains constant as it moves from A to B. Quite a common mistake to write in here is because it's not accelerating, but that's not really the explanation. So the reason it's not accelerating as it moves from horizontally is because there are no forces acting. Horizontally. So on to part 2 of A. The ball loses some of its kinetic energy when it hits the wall at B. It leaves the wall horizontally, and from the previous bit of the blurb it says that it strikes the wall horizontally. That's going to be important in a moment. So on figure 4.1, sketch the path of the ball between bouncing at the wall and hitting the ground. So what we need to be doing here is realising we're going to still have a parabolic motion, but because it won't be travelling as quickly horizontally, it won't get as far as A, so it's going to be underneath the curve that's already drawn in. Now if we go on to the second part of this, explain how the time taken for the ball to travel from A to B compares with the time it takes to travel from B to the ground. Well, the simple answer there is the time is the same. And that may not be too intuitive to begin with. If we think about it, it's moving in horizontally, so at point B it's got 0 vertical velocity, and the acceleration is only in the vertical direction, and the time it takes in flight is purely governed by the vertical component. So the fact that it's coming out at a slower speed than what it came in at horizontally, velocity I should say, it has no bearing on how long it takes to come back down as the time it takes to go up, because the air resistance isn't there, so that we're not going to have any effect on it at all. So we're going to want to say, just to finish this bit off, the time is the same because the vertical distance is still the same. In both cases. Okay. Now let's look at part C, which shows a tennis ball moving up a smooth ramp at time t equals 0. And it gives us a graph. It's a velocity time graph. And of course, every time we get a graph, the first thing we're going to do, what are the units? Well, that one's in seconds, and the velocity is in meters per second. So we haven't got any little tricks. Well, they're not trying to trick us with those, but we've checked it, so that's good. Now let's have a look at what the question is asking. So it's going to say, without calculation, the motion of the ball, we've got to describe the motion of the ball between time equals 0 and time equals 3 seconds. So what we need to be looking at here, because this is a velocity time graph, what I can see is that the velocity is decreasing, and it's decreasing at a constant acceleration. So what we want to say, and you've got to be very careful with how you word this, I would personally say the ball has a constant deceleration, and I would also then say at t equals, I think that's about 1.5 seconds, it comes to a stop. So that's this point here where, of course, the velocity is 0, and then the ball will be rolling back. And I'd be tempted to say with a constant acceleration. What are the points to make with these kind of ones? What they don't like is when you say the ball is constantly accelerating or constantly decelerating, because that doesn't give the fact that we've got a uniform acceleration. Because you could be decelerating, but the acceleration could be changing, but it's constantly accelerating. So just be careful with that. So with these, you really must say the ball has a constant deceleration and a constant acceleration, or you could say a uniform acceleration, and that would be perfectly okay. Right, let's move on. Now we've got to calculate the maximum distance, d, travelled by the ball up the ramp. Now, because we've got a velocity against time graph, what we need to realise is that the distance, or the displacement, is the area underneath the graph, and the maximum distance will be, well, it's going up the ramp, and then it comes to a stop at t equals 1.5 seconds, and then it comes back down. So the maximum distance it goes will be the area of this triangle up until the point where when it comes to a stop at t equals 1.5 seconds. So we've got to calculate the area of that. Well, that's nice and simple. We've got a height here of 4 meters per second and a time of 1.5. So the distance here is going to be the area under the graph, which is going to be half of 4 times 1.5, and that comes out at a distance of 3.0 meters.